Okay, so what we're going to do today is go over the quiz, review for the test in the short time that we have. You all right with that? Okay, so we've got our quiz. First question, we have a race car that has a track of radius 174 meters. And it's moving with the speed of 24.5 meters per second. So I saw a lot of people trying to calculate the centripetal acceleration. That's not what you have to do here. All we want is the angular speed. The angular speed from our definition is the velocity divided by the radius. When we do that, that's 24.5 meters per second divided by 174 meters. So when we do that, that comes out to be 0.14. And then the units on that, which is where some of us were messing up, are not revolutions per second, right? The meters cross out, and what I'm left with is 1 over seconds. What did we say that 1 over seconds was? Radians per second. Radians aren't a real unit, they're just a placeholder. So getting 0.14 radians per second is in radians per second. All we have to do is divide those two things. Okay. If we do this definition, it's going to give us radians per second. We don't have to worry about that. We don't have to make any sort of conversion if it doesn't specifically say revolutions in what we're doing. And a lot of you were making that conversion after you got 0.14 radians per second. You went ahead and multiplied it by 2 pi and divided it by 60. We were already where we needed to be. So be careful with the units that you're given, and remember that a 1 over second is the same thing as a radian per second. Okay, second one. So, I don't know how to write this down without having to think. For the second question, the speedometer is proportional to the angular speed of the wheels and if we have larger wheels, what happens to the speedometer? Probably shouldn't just leave that as speedo. That would not be great. Special thought language. James. You guys go. I'll email this out. All right, so if we have larger wheels, whoop, there goes that. We want to know what happens to the speedometer reading if we have larger wheels. So, what's going to stay the same when we have larger wheels? Angular speed. So we're going to set this up by saying that the angular speed remains the same, right? Because the speedometer is reading angular speed. So this is the speedo before, and this is after. Is everybody okay with that? Because it's still going to have the same angular speed that it reads, but if you're in your car and it says 70, we want to know what it looks like. So angular speed is velocity, and so we'll say velocity for the larger tires, for the larger radius, is equal to the velocity for the smaller tires and the radius for the smaller tires. So what we're looking for, velocity of the larger thing is going to be the velocity of the smaller one times the radius of the smaller one divided by velocity of the larger one. So because this is smaller than this, all of this is going to be less than what's going on. So what you read on the speedometer with larger tires is going to be less than what it read before. We're in Carrollton and it's not that country, so not a lot of people are getting lifts on their trucks and upgrading to bigger tires. But in Mississippi it happened a lot, and so this was a consideration. There's a lot. Have you been in one? Have you noticed the difference in speed? It's significant, even if you're just going from like a 28-inch tire to a 33-inch tire. It's a big deal. So, okay, question 3. Find the moment of inertia of a sphere if it's rotated about its edge as shown. So if I've got a sphere here, I want to know the new moment of inertia if it's rotating about this axis. So if we're rotating about that axis, my pivot point is not going to be at the center of mass. That's my pivot. And that's my center of mass. And so this distance is going to be the h that we're going for. Because the pivot is not the center of mass, we have to use the parallel axis theorem. So, the rotational inertia about the center of mass is 2/5 mr squared. Our h is that distance right there. What does that make the h? That makes it r. So plus mr squared. So 2/5 mr squared plus mr squared, 7/5 Mr squared. So the important thing, one of the important things about using the parallel axis theorem, and this is probably the most complicated part of the unit, is the parallel axis theorem, I would say. It's what you struggle on with the quest the most. It's what you struggle here the most with. We must replace this h term. We have to figure out what it is. Once we figure that out, we can stick it in there. All right, question 4. Question 4 is the stick being pivoted at its end. And then a sphere at the end over there. And what we're told is that the length of the stick is going to be L. The length of the stick stops at the end of the stick before we get to the sphere. And then that the radius of the sphere is equal to L over 9, or 1/9 L. You all right with that? So how many objects do we have here? We got 2 objects. We've got the stick about its end, and then we have the sphere. So the pivot for my system is right there. Is that pivot at the center of mass of the sphere? No. Is that pivot at the center of mass of the stick? No. But it is at the end of the stick. And since sticks are rotated about their ends so much, we've memorized the result of the parallel axis theorem for that spot. So every time we have a stick about its end, the moment of inertia for that is going to be 1/3 the mass of the stick times the length squared. Done. We don't have to do anything with that because it's a stick about its end. No questions asked. And then we have the sphere. Is the sphere being rotated about its center of mass? So we should write that down. So the sphere is not rotated about its center of mass. If that's my pivot, the center of mass for the sphere is there. So for the sphere, I have to do the parallel axis theorem. The the moment of inertia about the center of mass plus mh squared. So the moment of inertia about the center of mass for a sphere we have memorized, 2/5 Mr. squared, plus m. Now we got to talk about what h is. Yeah. H is the distance from the pivot all the way to the center of mass. So that includes L, and it includes the radius. So we have L plus L over 9. And we should substitute for what the radius of the sphere is, 2. That's also L over 9. So I got 1/3 ml squared plus, James, you have a note that says you can go talk to UTD. I'd go ahead and take your stuff. You already had your phone, you didn't turn it in. Okay, so 1/3 ml squared plus 2/5 m times L over 9 whole quantity squared plus m, and then what's L plus L over 9? 10L over 9, whole thing squared. It's really tempting to just square both of these. You're not allowed to do that. When you square a parentheses and you got a plus sign in there, you have to do that FOIL thing from a while back, which is less than fun. Just add them together. So 1/3 ml squared plus 2/5 m times L squared over 81. We have to square both terms inside of the parentheses, plus m times 100L squared over 81. And so we can pull ml squared out of there. 1/3 plus 2/5 times 1 over 81. Would it be beneficial to see how that goes into the calculator? Yes or no? Sure. It's a fun trick. There's also that. So 1/3 plus 2/5 times 1 over 81 plus 100 over 81. And then we do math, frac for the answer. We get 1. What did I leave out? Oh, all right, sorry. Second enter, best friend ever. There we go. Maybe not ever, but it's a pretty good friend. 637 over 4 over 5. Got 2 of them. Nice. And we have to do ml squared for the final answer. And again, if you get down to here, that's fine. But I want you to square everything out. I want to see that you're doing that right. Because a big mistake that I was seeing some people make is they weren't squaring everything the right way. I want to make sure that gets squared the right way. It's not good enough to just leave that there. I want you to distribute it where it needs to go. All right. That was the quiz. So, for this unit, you want to pull out some notes for something. We've got a test tomorrow. Yes, ma'am. Yes. So we got a test tomorrow. So we're going to do rotational kinematics, and we're going to do moments of inertia. Rotational kinematics, we're going to go from the linear stuff, x, v, and a, to the rotational stuff, theta, omega, which is not a w, and alpha. And for our definitions, we're going to say that theta is x over r, omega is v over r, and alpha is a over r. And it's the perpendicular part of x, the perpendicular part of the velocity, the perpendicular part of a, because we're talking about going around in a circle. Sorry, I want my circle to be good. So if my circle is spinning with some angular velocity, the speed at any point is going to be directed tangentially to the circle. It doesn't have a choice. That's the direction you would be going in at that point. This would be your radius. So your velocity would be defined as the radius times the angular speed. But in this case, the velocity must be perpendicular to the radius. By definition, it has to be. And the same goes for all of those quantities. The velocity, the position, and the acceleration are all perpendicular to the radius. Theta is going to be measured in units of radians. Omega is going to be radians per second, and alpha is going to be radians per second squared. Radians don't have a unit. This is what we saw in that first question on the quiz. Omega is V over R. So it's going to be, as far as the units are concerned, meters per second divided by meters. Just 1 over seconds, which is the same thing as radians per second. Got to keep that in mind. If we are given revolutions, it's important to know that 2 pi radians is equal to 1 revolution. 2 pi radians is once all the way around the circle. That's sweeping out 360 degrees, or 2 pi radians. That's the conversion that we would have to use. Now, because we have the same relationships between theta, omega, and alpha as we do x, v, and a, we can change all of our kinematic equations. So because we know that omega is theta over time, and alpha is omega over time. Well, first off, that tells me that if I have a graph of omega versus time, the slope is equal to alpha, and the area is equal to delta theta, just like we would have with a velocity versus time graph, being slope equal to acceleration, and the area being equal to delta x. And since this is where we got our kinematic equations, we can rewrite all of the kinematic equations to be angular. We can use them just like we did before. So the things that are going to come up are questions where you either have to use the graph or the equations to solve a problem. Questions where you have to convert between meters per second to radians per second kind of thing. Or questions where you have to go from revolutions to radians. And we've had lots of practice on all that. It would be a good idea to look at the released quest stuff that goes along with it. The other thing that we talked about a lot, was moments of inertia. For a single object with no dimensions, just a point mass, the moment of inertia is mr squared, where m is the mass and r is the distance from the object to the pivot point for a single object. But we don't always just use single objects. There are a few that you just need to know. And if I'm saying you just need to know it, I'm probably going to test you on that. Hint. So we have a rod at its center, a rod at its end. A rod at its center is 1/2 ml squared. A rod at the end is 1/3 ml squared. And then we have ring, disc, and a sphere, all at their centers of mass. So a ring is going to be mr squared, a disc is going to be 1/2 mr squared, and a sphere is going to be 2/5 mr squared. You just need to know those 5. And then the overall trend with all of this is that as mass moves towards the center, I decreases. Everybody good there? The more mass gets closer to the center, the smaller our rotational inertia is going to be. Now, life's not fair, and sometimes objects are not rotated about their center of mass. So we have to use the parallel axis theorem. So, for when an object is not rotated about its center of mass, we have to do this. And it's taking care of the 2 motions of the object. This is the moment about the center of mass. And this is the whole object treated like a point mass going around a point. It looks just like this. It looks just like I equals mr squared. So it's the total mass about the pivot. And the super important thing here is h. It's the distance from the pivot to the center of mass. We always have to find h and substitute for it. Always have to figure out what that h is and stick it in there. Okay. And then just like adding masses together, if I have more than one object, we're just going to add the moments of inertia together. So with this, I'm going to have you do questions where you're doing the parallel axis theorem. I'm going to have you do questions where you're adding objects together. There'll be conceptual questions on what happens as we bring the mass in. That kind of thing for moment of inertia. Okay. And then remember that you can use the math frac thing when things get hairy. Or not. You don't have to. You can leave it as a complicated list of fractions added together. That's okay with me. You don't have to have a pretty number, as far as I'm concerned. Am I all right with that? You guys have any questions? No? Pretty basic. My suggestion for you for studying is to look over the quest assignments. There are a lot of practice problems there, especially the ones that we didn't do well on. You have access to all of those as well as access to the solutions. Right? So if you want those solutions, I can print those off for you, the detailed solutions. Otherwise, just look it up online. For the Quest. Like your personalized solutions. I think I can look that up and print it off. So, are there any other questions?